is to provide an introduction of Chapter 2 project, which is Cardano's method. So before we get there, let's review quadratic formula and De Moivre's theorem. So for quadratic formula, for any quadratic functions, which is ax squared plus bx plus c equals 0, we can find the number that we plug in for x to get 0 by this quadratic formula, which is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So if you have any quadratic formula, how can we find the number to plug in for x to make everything equals to 0, making left side equals to 0? We need to use this quadratic formula, and we can easily find those numbers. The goal of this project is to find some formula like this for cubic functions. So that's the big goal of it. But we need a De Moivre theorems, which is, it says, for all real theta, which is the degrees or angles or radians in radians, angles in radians, CIS theta to the nth power equals CIS times n times that degrees or radian. Okay, keep that in mind. So ever since someone found the imaginary number, which is the square roots of negative numbers, in first half of 16th century, many people were interested in finding the formula that will let them solve cubic equations. So these two guys, Cardano and Bombelli, and other developed an algorithm for solving cubic equations. But when they apply the method to cubics that have real roots, like x to the third minus 15x minus 4 equals 0, they sometimes end up with expressions that involve square roots of negative numbers. So x cubed minus 15x minus 4 equals 0. So those Cardano and Bombelli and his friends realized that this equation has the same form as the identity, which is r plus s to the third power minus 3rs times r plus s minus r cubed plus s cubed equals 0. So the x part is r plus s, and the coefficient is 3 times r times s, and the x is again r plus s, and the last term is r cubed plus s cubed. So if you can find what the r and s is, then that's going to be the number that we're going to plug in over here. So that's how we're going to look at it, right? So if I cover this one, that looks like x, and if I cover this one, that's going to look like x, and if you cover this one, that should be equal to 4. So if you compare these two equations, you realize that this 3rs and this 15 corresponds, so it should be 3rs equals 15. Also, this 4 and this r cubed plus s cubed should be equal. So r cubed plus s cubed should be equal to 4. From this simple equation, we know that r times s equals 5. And if you cube this one, then we'll have rs to the third power times 5 to the third, which is r cubed s cubed equals 125. Also, we know that r cubed, if you add those two numbers, you get s. But I want you to realize that from Algebra 1, that when we have x to the second power plus 6x plus 5 equals 0, we can factor this out by looking for two numbers to add up to 6 and multiply to 5, which is 1 and 5. That's how we factor it out for the simple quadratic equations. We have very similar structure over here. Some number plus some number equals 4, and that number times the other number equals 125. So we can rewrite that as y minus 4y plus 125 equals 0. And using the quadratic formula, plugging in a equals 1, b equals -4, which is the coefficient of, I'm sorry, this is y squared, -4, and then also c is 125. Long story short, we'll have y equals 2 plus 11i, or y equals 2 minus 11i. And we know this i's could be, I is, we just replaced with r cubed and s cubed. So it could be r cubed, could be 2 plus 11i, or s cubed equals 2 minus 11i. So, we are not really sure how those mathematicians in 16th century found the value of r and s, but we definitely can use De Moivre theorems, which De Moivre actually was born 100 years later after they were talking about, so they couldn't use De Moivre theorem, but we can. So let's use that. Okay. So we know that we have r CIS theta, and we know that if you cube it, so we'll have r CIS theta to the third power, then we'll have r cubed CIS 3 theta, right? And we know that we're going to look at 2 plus 11i, which in a complex plane, you go 2 to the right from the origin and go 11 up, somewhere over here, right? And the r is the magnitude, which is the distance from the point to the, from the origin to the points. So if you look at it, this is the right triangle with 2 for the base, and the height is 11. So using Pythagorean theorem, you'll find that magnitude, or the hypotenuse of the triangle, is square root of 125. So square root of 125 is equal to r cubed. But we know that this square root of 125 is square root of 5 times square root of 5 times square root of 5, which is square root of 5 cubed. So we can cancel out both sides, so we'll know that r equals square root of 5. And how do we find the theta, which is the angle, right? So that is the tangents. So tangent of theta equals, we know that it's a slope, which is 11 over 2, rise over run. Now we want to undo the tangents, so we're going to use inverse of tangents. So we'll have theta equals tangents, inverse of tangents, 11 over 2. Okay? So let's say the CIS is, let's say it's alpha, right? Alpha equals 3 theta. So that means this theta should be 3 times, we're going to have to divide it by 3, because alpha equals 3 theta, and if you divide it by 3, the theta we'll know it's going to be alpha over 3. So this theta is actually alpha over 3, and if you multiply the tangents, I'm sorry, that should be 3 theta times 3 theta should be 3 theta. So this should be, this equals to inverse of tangent of 11 halves. So this 3 theta should be equal to inverse of tangent 11 over 2. So dividing by theta, this theta by 3, using the calculator, we'll find out that this theta will be equal to I'm sorry, this should be this theta should be equal to tangent of alpha over 3, which equals a half, using the calculator, right? Because we have this right triangles with square root of 5, then alpha over 3 or alpha third equals 1 and 2, because 1 squared plus 2 squared equals 5. So alpha over 3 equals tangent, inverse tangent of 1/2, and multiply, not multiply, but if you take tangent to both sides, then you get tangent alpha equals 1/2. That's what we get over here. So in exercise 1, you'll verify that this answer is exact. So just write it down. R equals square root of 5, which is the magnitude of the, right? Square root of 5 CIS theta, where we know theta equals alpha over 3. So we have square root of 5 CIS alpha third, which equals square root of 5 is cosine, right? CIS is cosine of alpha over 3 plus I sine of alpha over 3. And we know that this cosine alpha third, or this alpha third equals square root of 5. This alpha third equals tangents, inverse tangents of 1/2, right? We just found out from the previous of this thing. So we're just replacing alpha third with inverse tangent of 1/2. So we have plus I sine times inverse tangent of 1/2. Okay? And we know that the inverse of tangent is theta equals sine theta over cosine theta, right? So the inverse of tangents is the flipped version of it, so it should be cosine theta over sine theta. Applying these strings to this equation, we'll have square root of 5 times this part will be the cosine inverse tangent of 1/2. This part will be 2 over square root of 5 plus this I sine tangent inverse of tangent 1/2 part will be I times 1 over square root of 5, which if you distribute square root of 5, those are going to cancel out, so we'll have 2 plus I. So this is what the R is, 2 plus I. And if you do the same thing for S, you will find out that S equals 2 minus I. So as it says over here, what about the other roots? So we just found out that the 2 plus I and 2 minus I, which if you add them, right, if you add these two, then 2 plus I plus 2 minus I, then we'll have I plus negative I, which is 0, and 2 plus 2 is 4. So we know that these two will be 4, and so that's going to be 2 plus I and 2 minus I if you add them, which is 4. And if you plug in 4 to x to the third, right? So we have x cubed. Original equation was x cubed minus 15x minus 4, right? So we're going to plug in 4 for x because we just found out r plus s is 4, right? So r plus s is 4, so we're going to plug in, and we'll have 64 minus 60 minus 4, which equals 0. Good. So 4 is one root, but fundamental theorem of algebra said that if you have a cubic function, for example, then you should have 3 roots, including complex numbers. So we should have 2 more. And it says, of course, you could just divide x cubed minus 15x minus 4 by x minus 4 and get a quadratic and solve it. Then we can find out. But the goal of this project is to find a general method or the formula for cubic functions. So let's go back to the equation r cubed minus 2 plus 11i and s cubed minus equals 2 minus 11i. There are 3 roots to each equation. You have found one for each, which is alpha, which is, we said r here, which is 2 plus I for the first equation, and beta, which is 2 minus 1 for the second. But in investigation 2c, you have seen that if w equals negative 1 plus I square root of 3 over all over 2, then w and w to the second power are cubic roots of unity, so their cubes are each one. In other words, the 3 roots of r cubed equals 2 plus 11i are alpha, w alpha, and w squared alpha. So if you multiply this one, and if you have w, and if you know what the alpha is, you multiply, well, one of them is 2 plus I, and the other one will be this negative 1 plus I squared over 3 all over 2. If you multiply them, this guy and this guy, that's going to be another roots. And also the third roots will be this guy, negative 1 plus I squared root of 3 all over 2 to the second power times alpha, which is 2 plus I. So if you do that out, you're going to get the roots for this equation right here. Likewise, if you do that for beta, 3 roots will be beta and w beta and w squared beta. So we have 9 choices that the roots of the original equation corresponding to the possible values for r and s. So this is the introduction of the chapter 2.